PAL. So we have PROM, we have PAL, we already discussed that. We discussed what? PROM. We discussed PLA, programmable logic array, and the programmable ROM. If you can remember, in PROM, it is 8 times 4 PROM. When we talk about it, it has a decoder circuit. Then out of the decoder circuit, this is the output of the decoder circuit. Then we take the input and give it to the OR gate. Give it to the OR gate. So this is the input, this is another input. So 3 times 8, for example, you have 8 inputs, outputs here, right? So in case of PROM, we mentioned that output of the AND gate and the OR array can be programmable. So we can program anything here. But the AND array is fixed. That means between the input and the AND are fixed, and the output of the AND and to the OR array is programmable in case of PROM. In case of PLA, what we saw here, we saw implement this, and then we bring that certain connections. So here, in case of PLA, both the AND array and the OR array are programmable. So we can program according to our requirement. Right? So this was, we already saw it's a small recap from our previous lecture. So this was the 8 times 4 PROM, where we can program the output of the AND to OR array, but the AND array input to the input and between input and the AND array is fixed. Here, in case of PLA, programmable logic array, both the input between input and the AND array and the output of the AND to OR array can be programmed. Today we are talking about programmable array logic. Here, it is just the opposite. Here, opposite of the PROM. So if I draw this block diagram, so this is the AND array, output given to OR array. This is the output, this is the input. In case of PROM, this one was fixed, this one programmable. In case of PLA, both are programmable. Now today we talk about PAL. Here it is programmable and this one is fixed. That means the output of the AND array to the OR array, that will be fixed. On the other hand, from the input to the AND array will be programmable. So this is the PAL, programmable array logic. So we can say that in this case, connection between the OR gate and the AND gates are fixed, right? Connection between the OR gate and AND gate, this is fixed. And so here each OR gate will have the fixed number of AND gates, right? So we can say the connection between the AND and OR is fixed. So we can say that there are number of connection or number of the input or the number of AND gate to the OR gate will be fixed. Something like this. they are fixed. So each, for example, here in this case, whatever I draw, here this OR gate have 3 AND gate outputs. So this will be fixed. So that means we already know what is the output of the AND gate, the number of minterms. So minterms are fixed. So we will have 3 minterms. The output of the OR gate is always keyword SOP, sum of product. So maybe it is AB plus BC plus CA, whatever it is, or CD, whatever it is. So it will be fixed. So here each OR gate will have the fixed number of AND gates. So now how many OR gates will be there? It depends on your PAL functionalities. If the PAL have 3 functions, it will have 3 OR gates. If the PAL has 5 functions, it will have 5 OR gates. But the OR gates will have fixed number of AND gates. That means the PAL OR gate will have fixed number of minterms.
Can you explain that diagram again?
So this is the overall programmable logic design. We saw that in programmable logic design we have 3 configurations. Either it's PROM, programmable ROM, or it is a PLLA, programmable logic array, or it is a PAL, programmable array logic. In case of PROM, connection between the input and the AND array is fixed. Connection between the AND array and OR array is programmable. So here you already draw the decoder circuit, right? 3 to 8 decoder. Inside the 3 to 8 decoder circuit, that means we are giving our input, and those connection of the AND gate are fixed. And then we take the output. 3 to 8 decoder, we take 8 outputs from the 8 AND gate. Then we give it to the OR array. So that portion is programmable. So between the AND and OR array will be programmable. On the other hand, in our last lecture, we talked about PLA, programmable logic array. In this case, both the in between input and the AND array, as well as the output of between AND array and the OR array will be programmable. Just we talked in our last lecture. And today we said that this portion will be fixed, but this portion will be programmable. So this programmable fixed means what? Here we are taking the output from AND array and we are giving to the OR gate. So output of the AND array will give to the OR gate. So this is fixed. And the number of OR gate depends on how many functions we want to provide with the PAL. If you want to provide 3 functions, you will have 3 OR gate. Now, if this OR gate has 2 AND gate, it can be possible. It is not necessary that they have to have same number of AND gates. This OR gate can be have 5 or 4, for example, 4, adjust to the 4. So this will be fixed. It is not necessary that they have to have the same number of AND gates, okay? It's not necessary.
Depends on minterms.
Depends on minterms. Depends on minterms. But typically I found that they have, if I'm not wrong, only 3 to 4 products. Typically they have 3 to 4 product stubs. 3 to 4 product stubs. Typically they have 3 to 4 product stubs. That means typically there will be connection between OR gate and 3 AND gate. I will come to that. So now what we need to program? The connection between the AND and the inputs. Connection between AND and the inputs. Here we have to program this area. So if you want to program this area, so just for example, I just choose the 3 minterms one, just for an example. Here we will give the input in both true form and complementary form. So here if I draw and we are tuning colors so that we can don't get confused. So here we have, so for example, A bar, B bar, C bar. Now we will give all the connections. Initially, there will be connection from all the true and complementary form initially. Okay? Initially, all be connected. Then we already know connected means there is a fuse in between the source terminal to the column line. Then what we need to do, according to our program, we can supply a high current so that we can bar down the fuses to make it logic 0. So in this case, we can say that if PAL has 3 inputs A, B, C, and each AND gate will have 6 programmable AND gate connections. So how many connections? Each AND gate will have 6 connections. A bar, B bar, C bar. So what will be the initial output of the AND gate? Initial output AND gate is 0. Because A bar, B bar, C bar. So all the initial output of all the AND gates will be always 0. Okay. So depending on the requirement or the application, inputs are connected with the AND gate. It is possible to generate, that means we can generate according to our desired midterms. If you want, for example, from here I want A, B and C. So I just want A, B, C bar, B. So what I do, A, so I should remove this connection, A, then B, then C bar, sorry, I don't have C, D, so this one. So I can remove those connections, I will remain this, keep this intact, so I get A, B, C. So depending on our requirement, we can easily determine our midterms here. Okay. In typical PAL logic IC, it consists of multiple such OR gate. As I mentioned, if I now draw the typical IC of the PAL, it consists of multiple OR gates. So let me draw, for example, so this is F1, this is F2, this is F3. Then we give this connection. Right? And then we'll have our those A, bar, B bar, C bar, B bar, A bar. So this is the very general configuration. So each OR gate will represent individual functions. So here we can say we have 3 functions here. And here, just for simplicity, I just maintain all the 3 OR gates have the same number of AND gates, 3 and number, but it can be changed. But typically 4 to 6 midterms, 3 to 4 midterms, that means typically it will have, each OR gate will have 3 to 4 AND gates. 3 to 4 AND gates. Okay. So if you can think about this PLA, in case of PLA, in our last example, in our last day, we talked about, we saw that we just use 5 AND gates, right? 5 AND gates. Of course, we can use maximum 2 to the power 3, 8 AND gates, because in our last lecture, if you can remember, we take 3 inputs A, B, C, then we give the 6 different inputs A bar, B bar, C bar, and we just think that we have 5 AND gates. Of course, we can take maximum 2 to the power 3, like 8 AND gates, but we choose the 5 AND gates. That was the advantage of PLA on the PROM, over the PROM. We can use less number of AND gates. But here we can see that in PAL, it is actually less than PLA. Here, as I mentioned, in typically the PAL have 3 to 4 minterms. What does it mean? It can have maximum 3 to 4 AND gates. In our last lecture, we talked about PLE, where we use 5 AND gates. I hope you can remember. We try to design the full adder circuit, full substructure circuit. So to design this full adder or full substructure circuit, we take the common, right? We try to minimize them, then we try to common minterms so that we can share. In our previous lectures, we saw that in the AND gate, it was something like that. If you can remember, I draw a little bit, I not draw whole punch. So like this, then we take 2 OR gate, right? 2 OR gate. So here, this is the minterm. These minterms can be shared with both OR gates. If you need these minterms, I can share both OR gates. That's how we use. But here, we cannot share the minterms. We cannot share the minterms. These are the minterms only given to this one. We cannot share. So this is kind of a disadvantage, we can say. So in the PAL system, the number of product terms generated is limited. The first point is limited, and we can overcome. But how we can overcome? So for example, just for example, say this function. For example, this function has a minterm AB plus BC plus AC plus A bar C third plus A bar B bar. It may be possible. So we have 3 functions. Out of 3 functions, this function 2 has a minterms AB plus BC plus AC plus A bar C bar plus A bar B bar. So it has 5 minterms. So to get 5 minterms, it's supposed to have 5 AND gates, but it doesn't have 5 AND gates. How we can do that? To overcome this issue, there is an option. It is known as feedback. Feedback of the output side, from the output side. So you can see here, for example, in this case, this function, of course, if the function has the similarity, or this case, it has a function AB, BC plus AC. And this function F3, for example, it has, for example, AC plus BD. Sorry, AC plus BC. So we need to create this one AB plus BC. So if you want to get the, so maybe this AND gate can give me AB. So I take A and B. Then this AND gate can produce BC. So B and C. So this is BC. And this AND gate can produce AC, A and C, AC. So you have it. Now what we can do here, we can take this output and give it to the feedback path. Give it to the feedback path with a buffer circuit. With a buffer circuit. Okay? And in that case, we should have another line. We should have another line like this. This known as F and F1. F and F1. So this connection will connect to the F bar, and this one will connect to the F. So we can get a true form and a complementary form. Now if I look at here, we have AB, BC and AC. Now this AB, BC and AC, we can see with the true form, this one. So if I connect this one, this angle to this line, then it will give me AB plus BC plus BC. Now we have done, now we need A bar, C bar. So A bar and C bar. Then we need A bar, B bar. Then we will have A bar, B bar. Then it can take this.
What if we don't have?
If you don't have, then we need to increase the number of gates, the AND gates, if you don't have. So this is the drawback, or the limitation. It has limited mean terms. It has limited mean terms. So what we can do, yeah, I'll come. What should we do? How we can minimize, or how we can do? I will show you one more example. Then let me finish this one. Then finally, this is AC, and maybe it is, for example, BC bar plus C bar. So it will be AC. So this is A and C. Then second one is BC bar, B, C bar, and finally CC bar. C bar. So CC bar will be 0. Sometimes, for example, we don't have this one. We don't have this one. Then we can say we are not using this. Output of this one is 0. And then actually CC bar also give you 0. Okay. Now let's try with one example. If the truth table is given, from the truth table you have to find out the functions, Boolean functions, and then you have to implement with this PAL circuit. Okay, let us finish here. You just choose randomly, okay? According, you can put your equations, then you just need to select it. So,
And we are putting that one 0, so though we are not using this.
that means you're not using. So 0 will remain no problem because it's an OR gate.
AC and C.
Okay, let me write down the table so that by this time you can complete your circuit. For example, we have this input. C. So ABC 0, 0, 0. So it's a 3 input. And for example, we have 4 functions here. We have 4 functions, F1, F2, F3, F4. So for F1, for example, we have 1, 1, 1, 1. For F2, we have 1, 1, 1, 1, 1. For F3, Finally for F4. So I'm not writing the zeros, okay? We have zeros so that it will be easy to understand. So I didn't write in the blank is the zeros, okay? So this is the truth table, for example, for some logic circuit. It has 3 inputs and it has 4 outputs. So as it has 3 inputs, that means in the AND gate we will have 6 inputs, the true and the complementary form. And we should have at least 4 OR gates.
So are those
functions.
randoms, those ones?
Yeah, these are the inputs. 002, 02, 111.
And this output is all randoms?
Yeah, for example, we get this function. You have to implement it. This is your circuit. It's a 3 input and 4 functions. You have to implement 4 functions with this one. So let me remove this one. Okay. So what we can do, as I mentioned, as we have less number of meters, less number of AND gates, we should try to minimize. We should try to get the minimize. So I first write down the min terms for the functions. So for function F1, we have logic high for 4 different min terms, right? 1, 2, 3, 4. So it is 1, 2, 4, 6. 1, 2, 4, 6. For function F2, we have 0, 1, 3, 4, 7. F2, 0, 1, 3, 4, 7. Right? For F3, we have 1, 2, 4, 6, 7. 1, 2, 4, 6, 7. And finally, for F4, we have 1, 2, 3, 5, 7. What we can do, we can use the K-map to minimize. So that was the very easiest one, right? To draw the K-map so that we can find the functions. So if it is the K-map for this one, so this is A, and this is BC 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Draw the K-map for every. So we have 4 K-maps for 4 different functions. So here 1, 2, 4, 6, right? 1, 2, 4, 6. So 1, 2, 4, 6. 1, 2, 4, 6. And here we can put here 0, 1, 3, 4, 7. can say 1, 2, 4, 6, 7. Right? Just let me know if you make any mistakes. Here we have 1, 2, 3. 1. So we just get the QMF. Then we have to simplify, right? Simplify. So to simplify, we have to make a group of ones. We can see we have a group of ones here. We have a group of ones here, and this is the single group. Right? For this group of ones, what you can see, A is changing, so it will not be there. Only B and C is not changing, so it will be C bar. It has B, C bar. For this one, A is not changing, and C is not changing, AC bar. And for this one, it is A bar, B bar, C. Right? Now come to this function. We can see we can make a group of these two, we can make a group of these two, we can make a group of these two. We cannot make any, we don't have any group of 4, right? 4 ones. So we have to group of 2 ones only. So if you go for this one here, A is changing, B and C is not changing. So it is a B bar, C bar, because both are 0. For this one, A is not changing and B is not changing. So it is A bar, B bar. And for this one, A is changing, B and C is not changing, and both are A1 in 2 forms, so it's BC. For this one, we can say, we can make a group of these two, group of these two, and group of these two, and this is the second one. For this one, A is not changing, and C is not changing, AC bar. For this one, only B is not changing, A is not changing, A bar, B bar. No, sorry. Here it is, this one is only A, is not changing. And here, what is not changing? A is not changing, A is changing, and B, C bar. B, C bar. For this one, A is remain unchanged, and another one, AB. C bar, B, C bar. And for this one, we have 3. A bar, B bar, C. For this one, finally, it will be C plus A bar.
So in the first one, it is AC bar.
Which one? For function F1?
AC bar.
Oh, yeah. Thank you. Are okay? All are okay? So, what you can see here, we have 1, 2, 3, 3 midterms here, right? 1, 2, 3. Here we have 1, 2, 3 midterms. Here we have 2 midterms. But here we have how many? 1, 2, 3, 4 midterms. But if we want to design with the previous circuit, we have only 3 AND gates. 3 AND gates. So, but here we need 4. So how I can minimize?
F1.
Is there anything matching?
F1.
F1 is matching. You can see BC bar, BC bar, AC bar, AC bar, A bar, B bar, C, A bar, B bar, C. So we can write down this one F1 plus which one? AB, right? F1 plus. Now we can just design. So the F1 we have to feed back to the input. Take that one. It's the 2 form. With the 2 form.
Can you explain me why we cannot put 4, but in which part of the diagram we cannot put 4?
So here, as I mentioned, we have 3 AND gates.
Oh, 3.
3 AND gates means 3 midterms.
3 midterms. Okay. Why we cannot put another one?
We can, but for example, if you want to have, if you have just 3 AND gates, but if you want to add, for example, it is possible to implement this by using 3 AND gates. Why you will go for another AND gate? Because if you put another AND gate, it will have a power consumption. It will have due to the speed. It will increase your cost. So that's why. Is it okay? Should I need to draw? Or you can draw, right?
We can draw.
We can draw. Easy. But we should have a feedback form. That's it.
That's the last feedback.
Yeah. So this is the feedback form. This is one. So it will be similar like the previous circuit. Similar like the previous circuit. Okay? Like this one. So we have ABC, A bar, B bar, C bar. Then we just have the connection lines so that we can program here to give to the AND gate. So this portion is my programmable. And this portion is my fixed. As I mentioned, this is a PAL. The input to the connection between the AND array and the OR array is fixed. AND array and OR array is fixed. So we have 4 functions. We should have 4 OR gates. 1, 2, 3, 4. And here we will have 3 AND gates. Every OR gates have 3 AND gates, 3 midterms. But here we can see the function F3 required. The function F3 required 4 midterms. So we have to get a feedback here. Then we draw a line here, and we can give the connection to this one. Okay. So this is in general PAL circuit. So maybe you have to be given the truth table, or you will be given some functions, logical functions. You have to implement those functions. If you need to apply Boolean K-map, you can apply, minimize it. Then see which is your final midterms available. Can you share any midterms here or not? Then draw the circuit. In commercial, now I'm talking about just in general, in commercial, don't for your exam, but I found some information that's why I want to share. In commercial available PAL IC, they also have an output logic block. Sometimes in the commercial, this is the very basic one, right? But the commercial PAL IC, they have some output logic block. Output logic block means they also have some output logic circuit, some XOR gate or AND gate or NAND gate or NOR gate. So here it is something like that in commercial PAL IC. So this is the programmable AND array, as you already saw. The PAL, the programmable array is, the AND array is programmable, right? We give our, these are the input pins, IOP. So these are my input pins, 1, 2, 3, 4, whatever. Usually we get to the OR gate that are fixed. So we give it to the OR gate. OR gate. So here we have an OR array. But we should not take output from the OR array. Instead, we give another logic gate, output logic. These are output logic. take our output here. This box, so these are all array. Sorry. This box is known as macro cell.
This is all. Though this is not changed, or array is not changed.
Until here is changed, similar previous, right? We have a fixed connection between the and or. We have a programmable and array. Now, in our last example, we take our output from here. But in the commercial IC, they have some output logic here,
Like they have extra circuit.
extra circuit. So, overall, this one is known as macro cell, so that it can increase its functionality. It can increase its functionality. For example, just if I draw another example, it will be easy to understand for you. Very simple one. If we draw the simple one.
What kind of operation logic is put it in that?
Yeah, I'm showing you.
Oh, okay.
So the very simple one, for example, say these are the three AND gate we already draw last time, and we give it to what? OR gate, right? And we take the output here. So far we saw that. Then it is given to one XOR gate. The output of this OR gate is now given to this XOR gate. So logic gate. And another input of this XOR gate will be programmable. So now, for example, we have a function f here. When you give 0 here by program, so it will give you true from. If you give 1 here, it will give you complementary from. So this is the one of the simple example of that. I will show you more complex circuit, so don't worry. But this is the complex one. In the commercial IC, of course, it will not like be a pure IC, right? So it will have to have increased more different functionalities. So that's why it is known as, important thing is this block, total block is known as macro cell. This whole block is known as macro cell. Okay. So this macro cell can also consist of tri-state buffer or the encoder. For example, now I make it a little bit more complex. So I add a tri-state buffer. So that means I mentioned that this is overall circuit. Whatever you introduce here is known as macro cell here. So I here in this example, I just add one XOR gate, right? So this XOR gate is my output logic gate inside the macro cell. Then we add a tri-state buffer. We already know what is a tri-state buffer, right? We can design a tri-state buffer by using a TTL, a transistor logic. If the transistor is not on, then we have high input impedance. When the transistor on, it will pass logic 0. If you give the logic 0, it will pass 1. If you give 1, it will give you 0. So the TTL, the tri-state buffer. So, for example, we just connect a tri-state buffer circuit here, or the inverter circuit. Then I give it to the output. Then this tri-state buffer have to control. This control input can be a separate control input, or we can add another min terms to turn on it. It can be controlled by any way. It can be to control this tri-state buffer. We may have a dedicated input line, or we may have a min terms, whatever it is. So it's a tri-state buffer. So when it is a tri-state buffer, when control input is 0, when the control input is 0, the tri-state buffer will not act. So it will act like an open circuit or impedance, high impedance. When this control circuit is 1, this tri-state buffer will turn on. And now it will act like, why? If we have an F here, we will get F bar here. That's because this is an inverter circuit. So when control input of the tri-state inverter is 1, that it will give you the complement of your input. And when the tri-state buffer control input is 0, then the transit buffer will be detached. It will actually detach the input side from the output side. It will detach whole circuit. And then, if you have this detached circuit, what actually happened, it has something like this in the PL circuit. Then you can actually give a return path, a feedback path, you can give some input to the AND array. So if it is happened in this PL circuit, this node is known as input-output pin. You can give input, also you can take output, IOP. So it can increase the functionalities. So this whole portion is actually from macro cell, with macro cell. Okay. If we want to increase more functionality, for example, so far we have talked about this PLD, programmable logic device. We talk about PROM, we talk about PLA, we talk about PAL. All of them are combinational circuit. None of them are sequential circuit. That means none of them have any register. None of them has any memory cell. But in PAL, in the commercially available PAL, they also have a register circuit. That means they are sequential circuit. They can store, they can give the feedback, they can give you the information back. That is the feedback, right? In the memory cell, JK flip-flop or D flip-flop, what we do? We put the hold, store the information, and in the next stage, we also can give feedback to the board. So that is the more realistic one. So far we talk about this, the very general one. They are just only a combinational circuit. They are not a sequential circuit. So if you want to make a dry sequential circuit, what we need to do? We have to add some flip-flops. We have to add some flip-flops here. So here, for example, now instead of an inverter circuit, we have a flip-flop circuit. A very simple flip-flop circuit. For example, a D flip-flop. The data flip-flop is a very simple one. And just one input, and just either it will give you Q or Q bar, right? Q or Q bar. So with the clock, there is a clock, then this is D input, then we will have Q or Q bar. Then this Q and Q bar will be given to your inverter circuit, and then we will give you our output. So we are making a little bit more complex. This is still in the macro cell. In the macro cell, we have nothing previously. Previously, we take output from just here. Then we try to understand, okay, if we put another logic gate, here we add the XOR gate, we see that we can make the functionality in just two forms and a complement form. Then we add the buffer circuit. Then we said, okay, here now we can use as a high impedance inverter circuit, then we can give the input back. Now we are adding a memory cell here, so that we can even store that information, so that we can give to the next stage that information. So here the output of the XOR gate is connected to the flip-flop, and depending on the rising or falling of the clock, the flip-flop will give the input to the inverter circuit. Okay. Then through the tri-state buffer, this output of the flip-flop will be available at the output. Now I will draw the more latest and complex PL IC, which is known as PAL22V10. PAL22V version 10. Let me draw first, then I will describe it, okay? Give me some time. Let me draw.
This is included?
No. I'm just talking about the applications, how we do this. I already mentioned. Don't worry. Okay. Just for example, we have this circuit. Then we give it to this memory cell. We have clock and Q bar. Then here I give this Q and Q bar to a point of mux. then this output is given to a inverter circuit, tri-state copper circuit, then it is given to the. So here they mention in this to give one person this tri-state buffer to control, to activate or deactivate, they use another meter. And as this is a 4 to 1 mux, so it has two more inputs. It has two more inputs. The inputs are coming from here, one with bubble, one with here. Okay, fine. So to control this mux, we should have a selection line. Two selection lines because here is 4 into 1 mux. So it has selection line. This is the selection line, say this is control 1, control 0. Okay. Then it has another 2 into 1 mask. The 2 into 1 mask, one of the input is coming from Q bar, another input is coming from this one for the feedback. Then it is given to this buffer circuit. So it has also a selection line. See, so this is S1, this is S0. So this is the IC, a PAL 22 version 10 IC. It is known as a fully configurable macro cell. A fully configurable macro cell. It can do so many functionalities. It has so many functionalities. It is possible to configure the output as either combinational circuit or the sequential. They mention it register output. A register output. Okay. Through the control output, look at here now. Through this control output, so this is our control output, C1 and C0. It is given to this one. So this control output, we can actually select any of the input of the mask, right? S1. So we have S1 and S0. So through this control pin, CO, C1, 4 to 1 mask can be used for 4 different functions. When S1 and S0 equals to 0, 0. When it is 0, 0, it will select this Q. So if it is a Q for F, for example, then it will give F here. Then if it is control input is enabled, tri-state buffer is enabled, it will give you F bar. This is the one function. So that means it is giving you the registered value, right? From the register, it is giving you the information, register function. Okay. What about at this time? At this time, what will the 2 times 1 mux will do? As you can see, this is also S1. So S1, for example, the C1. Okay. So S1 is equals to 0. So as S1 equals to 0, so the Q bar output of the flip-flop will be feedback to the input side. At this time, as this is the true input, when it is 0, it will take this one. So this input is now coming back to here. The registered output is given feedback. It is the registered output. Okay. So the present state of the flip-flop will be available at the additional input for the AND gate. Present input with the flip-flop will be given as an additional input to the AND array. Next, when S1 and S0 is equals to 0, 1. 0, 0, 0, 1. In this case, what will happen now? Q bar will be selected. First time 1, 0, 0, it was selected. Now this one will be selected, Q bar. And if the tri-state on here, so you will get F here now. Because it is F bar, Q bar, so it will now inverting, it will give F. Since still the S1 is 0, S1 is 0 still, So we'll give the, whatever that information, it will give you the feedback to the end array. The third one is S1 and S0, 1, 0. In this case, the mux will select the OR output. It will not take the input from the register. So it is not sequential, conventional. So it will take the OR gate output. So it is coming to here. The previous two cases, it was taking from the memory cell. It is taking from here. And it will, if this tri-state buffer is on, it will give the inverted output. Okay? And same output of the feedback to go to the input. Because now S1 is equals to 1. So S1 is equals to 1 means now the mux will take from where? Mux will take from this way. Okay? Mux is taking from now this way. The OR gate from OR gate. And finally, when S1 and S0 equals to 1, 1, the F output will be, there is another function, F output, it will come to here, then it will go to there. So, all this function is available when your tri-state buffer is on. At the very beginning. Now, what will happen if the tri-state buffer is off? You put 0 here, your tri-state buffer off. Then it will just shut down all the connection. Then it will act like that as an input output pin. You can give your input to this 21 mux to this one. So it is known as, that's why this PL 2020 version 10 act as a fully functional power circuit. So we can do a sequential circuit, we can do a combinational circuit, we can take the feedback, we can also get the input output pin, use the input output pin. So this was actually, though I mentioned, that's why I talked about this one. In our regular lectures, we just mention simple circuits, one by one circuit, but in general, it will actually a complex circuit. So that's why I ask you to review the paper. It's supposed to be at least ADC and DAC, and on top of that, you should have some other circuitry so that you can know how the real circuit works. They will not only a simple one block. You have to separate the blocks, you have to know how they're working. Now we are looking here, see, we have the memory cell, we have the mark circuit, we have the tri-state buffer circuit, as well as the AND gate output. So this is an overall circuit. If you look at back at the very beginning, we talk about AND gate, we talk about our XOR gate, we talk about our mark circuit, right? So now if you can have maybe, if you take the signal, now you want to convert it to analog to digital, you can give it. Then you at the same hold it, memory, then for the next step you give the bit, memory, then convert it from digital to analog, then pass it to another places. So this is the overall it works. So that's all, as I mentioned. So for your exam preparation, this is the syllabus, but in next week also, we'll talk about some other stuff like this. What is the commercially available? What are the latest memory cells? I will talk about those things so that this is not belongs, will not cover for exam. Not worry, because I already give you the sample questions of how you can get a preparation for your exam. You can take the preparations for there. And if you have any questions, let me know. We can discuss in the next class. Another thing, I have a request for you. From tomorrow, the survey will start about this course. So please do the survey, and the survey will remain for 1 week. And there will be, according to our management, because the students are not very much interested to survey, so to encourage you, we decided to give you 5 bonus points. So they will give us the list. Who will participate in the survey, they will get 5 points bonus. But not only for bonus, please do survey, write down your experience, and if you have any suggestion for me how we can develop more this course, please let me know. Please join the survey.
The assignment should be handwritten.
Yeah. So survey will start tomorrow.
But
it will be closed by next Friday. So this Friday to next Friday.
But the assignment you told us we can type.
You can type, yeah. You can type, but not copy paste.
Oh yeah.
So we can check in the turn it on.
In the canvas here they have a system like if anything is copied from anywhere.
Yeah, so turn it on is there. So because mine is honest speaking, if you copy paste, it is not anything, I will not lose anything. I give you, as I mentioned, I give you this assignment so that you can understand how to use all the circuit together in a real life. So please don't copy paste. I ask you to handwrite or typewriting because so that you can at least read. If you read it, you will know how it is working. Otherwise, if you just copy paste, you will get your marks, but you will not know how it actually really working. So it's up to you. Okay, it's up to you.
What's the minimum number of pages?
No, so if you just review 2 papers, you can, so if you put up figures, actually it will take at least 2 pages or 3 pages, right?
Yes, sir.
Yeah. So I can read those things, I can check the turn it on. So the content, according to the content, I can see how much you actually give that vote. Yes.
So just we need to take a paper which is having ADC and DAC.
You 1 paper or 2 paper, so that you can get an idea. Not only, of course, the ADC, but I'm sure they don't have only the ADC and DAC.
Yeah.
They have the other circuitry.
So just
if they have the analog circuitry, you don't need to explain those analog circuitry. But if they have the digital circuitry, like any logic gates, any marks, any demarks, any decoder, any encoder, you can explain it.
So we should explain the paper.
Yeah.
Write a
Explain
small
the paper.
review regarding.
Yes, exactly. Okay. Anything else? I hope you enjoyed that course. I tried my best. Thank you so much. See you next week.